In this video, we're going to talk about how to interpret a derivative. Now, there's sort of a hint in the notation. The units of a derivative, if we want to know what the units are of your derivative, well, let's see. The notation for a derivative, dy over dx, rise over run. Well, let's see. The units are basically whatever the units are of your y variable divided by whatever the units are of your x variable. And really the interpretation is just it's the change in x over the change in y. So let's take a look at an example. For example, let's say you have a function where the x-axis here is the number of months since the pandemic began, and the y-axis is the total number of deaths due to coronavirus. The derivative is the slope, and so while the y value here is giving the total death count, the slope, or the derivative, is number of deaths, but then divided by the x unit, which is the number of months, so the interpretation would be the number of deaths per month. Similarly, let's say the y-axis is the total number of infections, and the x-axis is the total number of handshakes that happen in any given city or something. Clearly, the more handshakes, the more infections, but it's sort of exponential here. And so if we wanted to look at the derivative and interpret what that means, it's a number of infections that happen per handshake. So the units here are like per handshake, the number of expected infections that we can get, and it's going up sort of exponentially in this case. So now let's take a look at some examples that are more traditional in economics and introduce some concepts within economics in the process. So let's say you're given this function, also called a production function, which gives you how much output or product you have. Let's say if you're a car factory, then this output would be the number of cars you've produced. If you're a pencil factory, it's the number of pencils you've produced, and so on. And it doesn't need to be limited to physical objects. You could also think of more, if you're a hospital, it's the number of patients that you've treated. So that's the output. And then the input variables are L for labor, the number of people working on it, and K capital, the number of machines, if you will, that you have working on it. If you're given this production function, and let's say you're asked, find the marginal product of labor, the MPL. Well, here's where some notation and some vocabulary from economics. The word marginal in economics usually just means the next or last, sort of doesn't matter, next or last, but it's really whenever somebody says on the margin, they're not talking about the total or the average, they're talking about just the next unit. So the marginal product of labor. So, well, let's think about this. So if this graph over here is the graph of your production function, so again, let's say this is the number of cars you've produced, and this is the total number of workers that you have. Clearly, the more workers, the more cars are produced, and it's going up, but at some point it starts to flatten out where this 10th worker didn't add as much to your product as the very first worker did. So these slopes are called the marginal product of labor because it's just talking about the units, again, cars per worker. So it's really the marginal product, meaning the amount of cars, or again, whatever your output is, the marginal one, meaning just for the next one, per worker. So here, if I were to say, find the MPL, well, the MPL, marginal product of labor, is, first of all, mathematically, the MPL is just the derivative of quantity. But again, this is a partial derivative because there's two variables here, so we got to specify with respect to L, right? So the derivative of this with respect to L. If we want to find that, we just take the derivative. Notice here, k to the 2/3 power is treated like a constant because it's the partial derivative, so we're only treating L as our variable. So really, the derivative of L to the 1/3 is 1/3 L to the 1/3 minus 1 is negative 2/3. And then again, we have this k to the 2/3 as is, like a constant multiplied. So this is your MPL. If I were to say find the MPL, that's what it would be. And then, of course, you could think about questions like, is the MPL increasing or decreasing? Well, looking at this, we could rearrange this, and the MPL would be this 1/3. We got a k to the 2/3 on top. We also, this L to the negative 2/3 is like having an L to the 2/3 on the bottom. So if this is your MPL, your marginal product of labor, now we can say, what happens when the denominator, the number of workers, is 10 versus like 1? Well, it's going to be a lot smaller when there's 10 workers, which again, it's talking about the number of cars that worker is adding, the marginal product of labor. So so this output here is the total, but the MPL is the slopes here, so the slopes are going down. You could, of course, then also graph the MPL itself and say, all right, yeah, it's going down over time because that's the slope of this guy, right? Yeah, that's the MPL. We could also notice that what happens to your MPL when you just have more machines, when your K goes up. Well, if all of a sudden in your car factory you just buy a lot more machines, then no matter what the L is, that worker is going to contribute more because they have access to more machines. So the higher the K, the higher the MPL. But the higher the L, the more workers there are, the lower the MPL. That's called diminishing return. So here, and this is a concept that's true throughout a lot of economics, diminishing marginal returns. The more of something you do, the less value you get out of the marginal or the next one. And what that's saying in mathematical terms is that your derivative is decreasing. So it's not necessarily saying that your derivative is negative. Like here, your derivative is still positive. Each person is still adding a car, but they're just not adding as much. And so if you were to graph your derivative itself is decreasing, meaning the rate at which stuff is being added is going down. That concept extends to this notion of utility and marginal utility. Utility, we could think of that as it's relating to preference. And long story short, the higher your utility, the happier you are, and you prefer bundles of objects that give you more utility than less utility. So if you have a utility function, and it's given by this guy over here, u equals root xy, let's just put this over here, u equals root xy. So here you can think of x as, say, the number of apples that you consume, and y as the number of bananas that you consume. And so, long story short, what this is saying is the more of either good, the more utility you have. But if I were to say find the marginal utilities, that's basically saying the marginal utility with respect to x, get x, is just the derivative with respect to x. And so, personally, I would just rewrite this as x to the 1/2, y to the 1/2, and now I can easily find that partial derivative. With respect to x, I'm treating y to the 1/2 as a constant, so the derivative is just the derivative of this guy. So the 1/2 comes down, I have x to the negative half, and then I'm going to have y to the 1/2 times here. So this is the marginal utility of x. So that's that. And notice again here, you can rewrite this if you wanted as y to the 1/2 on top, over, and then we got this 2, and we also got x to the negative 1/2, meaning that's x to the 1/2 on the bottom, which means the more of good x you have, the less your marginal utility of x, meaning the less the extra happiness that each unit of x gives you. And this eventually will relate to a concept in economics called the demand curve, and it explains why the demand slopes down. It's because the third slice of pizza doesn't taste as good as the first slice of pizza because the marginal utility is decreasing. That's also true not just of consumer stuff, but also in general for government expenditures. The 10th dollar that the government spends on any given project is not going to give as much of a return as the first dollar that they spend, usually.